This is activity 212 from section 2.1 in differential equations. And this section comes right after talking about a damped oscillator, in which you take the second derivative and say, well, a second derivative is really, I can create two variables, x and then velocity, which is the first derivative of x. And then I can describe the system with two equations with only one derivative. And that actually makes it simpler mathematically to have two equations, one derivative each, rather than one equation with two derivatives. So here we're going to look at a simple harmonic oscillator that has no damping going on. And we're going to consider this function y equals cosine beta t. Under what conditions beta is y of t's solution? Well, the second derivative of y with respect to t plus k over m y equals 0. So if y equals cosine beta t, then y prime equals negative beta sine of beta t, and y double prime equals negative beta squared cosine of t. And so then plugging that in, you get negative beta squared cosine beta t plus k over m cosine of beta t equals 0. And so you get that beta squared has to equal k over m, which means beta equals positive or negative square root of k over m. But then it doesn't matter if it's positive or negative because cosine is an even function. And so if beta were positive or -1, it would give you the same function. So you don't need to worry about the negative square root of k over m. Okay, so what initial condition in the YV plane corresponds to the solution? Well, the initial condition is, well, y of 0 equals cosine of beta times 0 equals 1. And then v of 0, well, that's equal to y prime of 0, which is negative beta times sine of beta times 0, which equals 0. So it's the 1, 0 in the YV plane. Okay, in terms of K and M, what is the period of the solution? Well, it's the period of cosine is 2 pi, so it's going to be the square root of k over m times 2 pi. And then finally, sketch a solution. Well, I did that in Desmos. So here's y is cosine beta t, and v is negative beta sine of beta t. And so you see that if beta is really big, it looks like that. If beta is really small, it looks like that. But that's the solution. It's just going around and around and around. So that's our solution in the, so y is going where x goes and v is going where y normally goes, so it's in the YV plane. So that finishes that activity.